In this lecture, we're going to discuss Lab Project M4. Lab Project M4 extended what you learned in M3, working with multiple rungs of logic with multiple memory locations, but no I/O. In this lab project, we're going to introduce the use of memory locations that are controlled, influenced by external field devices like sensors or switches. The reason we did it in this order is first to establish in your mind that when the program executes, it executes using memory locations, no cognizance of I/O, period. All the ladder logic addresses memory locations, not I/O. A rung of logic does not go look to see what an input is. It goes and looks at a bit in memory, and that bit in memory may be controlled by the state of a screw terminal. So first you need to make sure you understand that when you execute ladder logic, it's executing solely within the memory locations, totally irrelevant at that instant of what the I/O is. Because remember that you learned from way earlier lectures that it goes out and it gathers up the state of all the inputs. It takes a snapshot of the state of all the inputs, puts that snapshot in memory, then the logic uses that snapshot. Well, as the rung's executing, the inputs can be changing. So at the instant that a rung is looking at the state of, say, input 2 could be in a different state at that very instant. Now we're talking about microseconds, milliseconds at the most, but you need to firmly understand this relationship. So this project M4 is strictly introducing input memory locations controlled by input field devices into the mix. So we're taking this one step at a time. Again, you can pause, do the lab. If you've already done the lab, then continue, or come back and watch it again. And again, don't go to the next subject until you've got everything so far really solidly locked down in your head. So let's go do this. Well, here we are in our fourth lab project, M4. You look up at the top there and it shows M3 ladder logic diagrams. First thing I'm going to do, because this is how we left our project, is I'm going to save it because I'm online. Then I'm going to disconnect. Then I'm going to rename it. So File, Save Project As, and I will make it M4 ladder logic diagram I/O, because that's what we're going to do. Okay, saved it. That way we know we're in good shape. I can bring the program back up. Notice that I lost some things I had over here. So we'll unpin that. So I'll drag this up, global variables, and then I'll open the local variables. When I say tags, I mean variables. So I use tags, variables, pointers interchangeably. None of those are memory locations. They all point to memory locations. Pointer was one of the original names because whatever text or numbers you use, it pointed to an actual literal numerical location in the memory array. And then variables, that's real good because it's a value that varies. So now we're lined back up here. Now another thing I want to point out is here's our simulator, okay? And I've got it slightly off the screen to kind of maximize the space. Now I don't have to have any of this to speak of visible. I could drag down the ladder logic until only a small portion of it is showing, and then when I want to use a simulator I could just click on it like that or click back there. So I'm going to kind of split the space right now so we can see the input terminals and the logic. Now in the first lab project, M1, we kind of explored the basic graphical user interface, connected components, workbench, and the data table. Then we went to a program and a rung and demonstrated a program with a rung and how that interacts with the program mode, the run mode, and what access you have from your keyboard with the mouse and from the internal bits. In other words, just toggling internal bits. And you look up right in front of you, that's all there is. It's internal bits. So you don't have any access to control any of that except from your mouse. You can go up on any one of these, and we're offline. Offline, there's not much you can do. But online, and we might as well go there right now. So we're starting out There's two ways you can do it. You can click on disconnected so it says connected, or you could have clicked up here, right here. See where it says disconnect? So you can disconnect from here and here. The grammar is in the opposite state. Now this is the output window, which is what we had open. So what's interesting about what just happened, when I went online, it went right back to the format and the spread out that I had for these different windows. We'll leave it like that. I don't have the local variables, so I'll run this up so I can see the fundamental. I really don't need this, except that we put it down there so it didn't keep popping up in front of our code. Now we'll go get the local variables, which there aren't any, unpin it, and drag it down here. Okay, so now we're all ready to fly here with M4. So you see we're sneaking up on this whole thing, first with the software, then with the data table, then with a few basic instructions and a single rung of logic. And then in the last lab, M3, we introduced 2 rungs of logic so we could demonstrate scan dependent logic. It makes a difference what order you scan the rungs and if there is an interaction between the rungs. And that was the case where we were addressing the same address in memory, the same memory location, with 2 different OTE or direct coil instructions. You don't want to do that. But it's an easy way to demonstrate last man wins or logic that's scan dependent. So the first thing we're going to do is we had you create a new name, and I'm going to go back offline now. So I'll save and then I'll disconnect. Now see here it says click to disconnect, connected. Okay, that's the state of it. If you click on that, it disconnects. Or you can go over here and it says disconnect. So it really doesn't matter which one you click on. So now we're disconnected. And what I had you do is change this to bit 16 to demonstrate something. So I'm going to put in a 6 and hit enter. And what I wanted to show you was, first of all, you get this little yellow triangle. That means something's wrong here. You need to fix it. Well, something this simple, you're going to know it's this. See, it's a name bit 16. Go over here, see, name bit 4 type Boolean. So that's your clue right there that this is not actually defined as a data type. It's not really a tag. It's just a name typed into that field. So bit 16 would not be a variable until you defined it. I'm going to right click here, go to variable selector because I don't want to use bit 16. Instead, I want to do our first I/O. So I scroll down to, and I could have done the same thing over here in a backwards way, but let's not do that. Let's do it from the variable selector, and we picked digital input 0. We say OK, and voila, there it is. So now we have a true if on instruction addressing a bit in memory whose state is set in the run mode by the voltage level at the screw terminal for input 0. Now, typically, I refer to inputs and outputs as input 0 or output 0. I don't say underscore IO underscore embedded IO or underscore digital input underscore 00. I just say input 0, input 1, output 3. And once we start buffering IO, that's another subject, then we'll actually name them IN00, IN01, etc. For right now, though, we've assigned one. Okay, now I told you to download. So we made one simple change. We went from all internal bits, in other words, non-IO bits, to accessing a memory location whose state is determined by the screw state, the screw terminal state, voltage-wise, in the run mode. So let's download. This always takes a minute. I'm going to start downloading with project values and uploading with project values just to avoid any conflict. But out in the real world, you may not want to download with values because you want to keep the values that you already had online. Now in our case, we really don't have much to play with, so it's not going to make any difference what we do. Now I like the fact that the output window jumped out of the view here and popped itself down there. So that was the reason we did that, so we weren't boogering up our programming space here, our logic space. So I had you download, and then I had you look at this rung, and the switch is in the off position. Well, what switch? Where's the switch? The switch is right here, see, on the controller. I had you turn input 0 on. I turned it on. That instruction is now true. This instruction says input 0 is on, therefore it's a true statement. This says bit 4 is on. It's false because bit 4 is not on. The question in the lab Does the switch connected to input 0 now control the true-false state of the instruction that addresses that bit in memory? Now, I said yes, then I said toggle it back and forth while observing the rung to verify. You could argue yes or no. You could say yes, indirectly the switch does, because it turns a screw terminal high or low, which changes the bit in memory that that instruction is addressing. But in the program mode it doesn't, so that's a gray area in answering that question yes or no. As long as you understand, yes it does indirectly, but not directly control it. The switch controls the voltage at the screw terminal, goes through an opto-isolator, gets scanned in, and that state gets put into memory. The state of that switched input indirectly controls that bit in memory. In the program mode, it does not, because it doesn't get transferred to that memory location. Then I had you right-click on this instruction and toggle Boolean value. And I want to demonstrate something. So I'm going to right-click here and toggle Boolean value. Went off and right back on. And the reason it went off is because I told it to go off. And the reason it went right back on is because the very next program scan, when it did the I/O update, it sees that that screw terminal is high through the opto-isolator, and then the scan in sets that at 1 or on. So it's just like any other bit in memory. If there's something already influencing it in the program or in the run mode, then no matter what you do to the keyboard, it's going to overwrite what you did. Scan is faster than the hand. And I ask you, does it change? Yes. Does it remain changed? No. Who dominates the state of that bit in memory? You or the electrical state of the field device connected to that screw terminal? Field device with an active scan. Answer some duplicity there. You could say in the program mode, I can mess with it, or I can go force it, in the physical value and lock that I showed you for forcing. But the straight up answer would be the field device does during an active scan or in the run mode. Right click on the instruction that addresses bit 4 and try to toggle that Boolean value. Well, we know what's going to happen here. It's going to go on and stay on, right? Did it change? Yes. Did it remain changed? Yes. Who dominates the state of that bit in memory? You or the electrical state of some field device connected to a screw terminal? You from your mouse and keyboard. Does bit 4 know who changed its state? No, it does not. A bit is a bit, and only you know who is controlling it, the programmer. Bit 4 doesn't know you toggle this on from the keyboard or from the mouse. This bit right here really doesn't know that it's controlled by an I/O point. It's just a bit in memory. However, we have executive software built into the controller that you can't see that's going to make that bit match the state of the screw terminal in the run mode. I think you understand that. Does bit 4 know who changes state? No. Okay, then I had you save and disconnect. So save, and you can disconnect here or over here. It really doesn't matter. Then I had you change a few of the memory locations. This remains bit 1, bit 5, bit 4, bit 2. Now this is bit 4. So we just click on that, click on bit 4, and we're done. As I read the first rung, input 0, bit 4, bit 2. Bit 1, bit 5, bit 4. Okay, save and download. Save. It's interesting that the save icon is still a 2.5-inch floppy disk. I haven't seen one of those in years, literally, unless I'm going through old boxes and I come across the 15 disk that it took to upgrade RS Logix 5000 back in the day. Download. Remember, download is a process of first compiling or building, then it downloads. So see, it says build succeeded. Now it's going to download. I'm going to download project values from now on because there's no reason that I would have something different offline than online. Not yet. Now I left that input on here, down here. See, input 0 is still on, because remember the simulator is apart from the program. The simulator's got nothing to do with the program. Now, that popped up whether or not you want to download or not. And I said in there it's important to know when the message pops up, do you want to download, do you want to do this, do you want to do that? That's another chance for you to think about what you're doing to make sure you're not messing anything up. Okay, now try toggling bit 4 from one state to another. Does it remain changed? Bit 4, of course I know what it's going to do, and I think you do already. Went on, right back off. Went on, right back off. But notice B2 never goes on. Okay, watch bit 2. For momentarily, it looks like the rung's true. And the reason that it does this, listen very carefully. You're not looking at what's necessarily going on in the controller. Remember, that all of this is just a graphical user interface. This is just dead graphics, that they are animating the color of this ladder logic. There is no ladder logic in reality in the controller. So when I toggle this on, momentarily, it is on, but the rung is never actually scanned to set bit 2 on. So bit 4 is on temporarily, and the reason it's on temporary is because down below in rung 2, false, true, so the rung is false. The false execution says bit 4, you're off. So here we turn bit 4 on, and you can see that it goes right here too. In other words, it reads it as on, but it doesn't execute in the logic. That's in that one scan right there. Then the very next rung, in the scan read, false, turns it back off. Okay, this is a very important concept to get a grip on, and that's why we did one rung with no I/O, and then we upped it to multiple conditions, one rung, and then up to multiple rungs with multiple conditions, and then we introduced the I/O. The question in the book, try toggling bit 4 from one state to another, does it remain changed? No. Why? Rung 2 true sets to on or sets to off. In this case, it sets to off. Bit 1 was already on, which didn't match what was in the book. So now if we do this, watch bit 4 in both cases. See, it shows off there just for a split second. This is how it was when you did your lab. I already had bit 1 off in the simulator when we started this project. So I hope that didn't confuse you. Okay, try toggling bit 1 and 5 from one state to another. Do they remain changed? That's 1 and 5. First of all, look around. Do you see anything over here that's controlling bit 1 or bit 5? That's your first clue. So if I toggle bit 1 on, this goes false. If I toggle bit 5 on, that goes false. Do either of them affect the state of bit 4? Yes. Do they remain changed? Yes. Who controls the state of bit 2? You from the switch position and bit 4? Or would you say you from the switch and you from the keyboard with bit 1 and bit 5? I would say input 0 and bit 1 and bit 5. If you hadn't thought about it already, I could take these two instructions right here, because these two instructions and the states of bit 1 and 5, they control bit 4, correct? So I could replace bit 4, true fine right here, with these two instructions. So this says input 0 and not bit 1 and not bit 5 controls bit 2. I could eliminate this whole rung down here. Now I'm not going to do that. I just wanted to point out that these two instructions right here and are the collective state of this rung controls the state of that bit. So we could put these two up here in that place and bit 2 would still behave the same, and there would no longer be a bit 4 in play. So we had you save and disconnect, and then we had you change this to an actual output, bit 2. So I'm going to go right click on this, variable selector. I'm going to go to I/O, micro 850, and then I'm going to pick digital output 0. Okay, and we have that done. Now we're going to download. We could save, then download. Download with project values. Now I show you my screen layout with the processor and the local variables all spread out here. I'm not even using the local variables because we made all these global variables. And if you wanted to find them, you can scroll down right there, bit 1, 2, 3, 4, 5, see? And I can turn off bit 1 right here. Let's try turning on or turning off bit 4. See? It won't stay because the logic overrides what I did with the keyboard, with the mouse. Okay, I had to save and download. And everything appears to be the same, but the rung number 1 is controlling the state of a different bit in memory, output 0. That of the bit that controls the state of the output field device that's connected to the screw terminal of output 0. Is this true or not? Yes, it is true. Flip input switch 0 back and forth. We'll go to off because we had it on. Does it affect the state of that output? Yes, it does. Leave it in the on position and try toggling the state of B1 back and forth. So I could go up here and do it. Then leave it in the off state, then repeat with bit 5. So we'll do it with bit 5 too, just so you see it. Okay, so we'll leave them both off. Bit 1 and 5 are off up here. Bit 4 is on, and we can't turn it off because the logic is turning it on. With input 0 on, which it is right now, does the state of either B1, bit 1, or bit 5 affect the state of output 0? Yes, it does, because it affects bit 4, and bit 4 affects the state of output 0. Now we had to save and disconnect again. Eventually we can go to online programming, so you don't have to save, disconnect, make your changes, and download it. But for right now, I want you to get really good at going on and offline to do your edits. Then we had you change some of the tag names or pointers or variables, and you needed to be really careful what you were doing. I could type in underscore IO, and voila, it pops up that category. And so I can click on that. Now I have digital input 1, and then we want digital output 0 here. So I could do the same thing, or I can just scroll to wherever it is, digital output 0. And then here we wanted digital input 2. And we still had bit 4. Output 0, input 2, input 1 on this state input 0, and that state output 0, and that stayed bit 4. So then we had to save and download. Download with project values. Now we have digital input 1 is off, digital input 0 is on. So I'm going to change it to match what's in the manual. So I turn on digital input 1, and that turns on output 0, but because output 0 is on, this rung is now false. What controls the state of digital output 0? Input 0 and input 1, ANDed. If digital input 0 and digital input 1, then digital output 0. They're ANDed together. If they're both on, true if on, then energize output. If output 0 is on, what can you say about the switches that control these two inputs, input 0 and 1? They have both switched 24 volts DC to those screw terminals, and it's in the run mode. That's what you can say. It might not be 24 volts DC. We won't just presume that. But both switches have switched logic voltage, high, to those two screw terminals, and because you're in the run mode, it controls the state of those two bits of memory, DI00 and DI01, and then that controls DO00. Now I had you try some different combinations, and I asked the question, can both of these two rungs ever be true at the same instant? The answer is no. Now you know this is kind of a matchup with a previous lab where we asked the same question, but the reason is different. In the previous lab, the first instruction in each rung was the same memory location. Rung 1 was true if on, and rung 2 was true if off, same memory location. That's what kept both rungs from ever being true instantaneously. But the thing is, if this rung is true and output 0 is on, then this is always going to be false, and the rung will always be false. So both rungs can never be true at the same instant. And again, remember, we're sneaking up on this. Can the state of a bit that controls a field device, an output, memory location, control the state of a bit, in this case B4, in memory, not connected directly to any I/O? Yes. You can see that the state of output 0, if I make either one of these false, output 0 goes off, this goes true and turns on bit 4. Can the state of an output and an input together control the state of a bit, in this case bit 4? Yeah, there's an output memory location, true if off, output 0, true if off, input 2. Now if I turn on input 2 from my simulator down here, that doesn't make the rung any less false. It was already false because digital output 0 is on, and the only way you can turn off digital output 0 would be to turn off one of these two inputs right here. Summary: a bit is a bit. Instructions read the state of bits and that they address. In other words, they address a bit in memory, they read the state, and then some write to the state of bits that they address. All instructions address memory locations, bits or words. Right now we're doing bits, but later on we'll do words. Something else that I had in the lab project book that, if you look close here, you can see the darker red square there. You can see two of them right there. You can see one there. You can see one there, darker blue right here, here, two there, and one there. These are all rung zone markers, and you don't do anything with them. But keep in mind that in some cases what happens in between two of them and what happens here is two different things. So this is the instructions logical state out, and this is the rung state condition at that point. See, it starts true no matter what. Look down here in rung 2. See, it starts true. Then the blue here says that that instruction is false. Therefore, the rung is false. See, this is blue, whereas up here it's red. Just for grins, notice that the difference here. In other words, this little space in between is red, and then it's got a little blue at the beginning, whereas here it's all red. So if I made it all false, then you see it's all blue. If I went back to turn this on, now you can see it's false coming in. You don't need to look at these little rung zone markers. I just noticed them one day, started looking at them. Why are they in there? Is that just graphics or what? So anyway, they do have some indication. That wraps up this lab project. So you got to be getting pretty good at this point where you can write real basic stuff. Now, we haven't gotten to any of the more advanced instructions. And actually, timers and counters aren't advanced. They're still basics. And actually, all we've done is true if on, true if off, energize output, and that's it. Or if you like, direct contact, indirect contact, and direct coil. So we still haven't gotten to latch and unlatch yet. That's coming up here pretty quick. Okay, so we finished up Lab Project M4. This should be becoming more interesting and more fun, or more enjoyable. There is no satisfaction like that is in this industry, in this venue. Nothing beats writing a rung of logic, downloading it, executing it, and it does what you expected. That makes you feel like you know what you're doing. Everybody likes to know what they're doing. So we're just going to keep on building here. That's it for Lab Project M4. We're going to go to the next step in this process. We'll see you for the next Lab Project and lecture.